I want to be able to look at a matrix, perform a calculation, and determine if it's invertible or not. The number that does that is called the determinant of that matrix. So if I have a 2 by 2 matrix, we've already figured out that this is the number I need to know. I'm going to call this the determinant of A. That's abbreviated either as the absolute value of the matrix or DET of A. And what we have come to already understand is that A is invertible if and only if the determinant of A is not 0. But we had this huge list of equivalent ideas, things that meant the same as being invertible. So if I wanted to look at a larger matrix, like this 3 by 3, then I could ask the same question. Is there a number that I can calculate from those things will tell me whether or not A is invertible? All right, let me think about the list of equivalences, properties of invertible matrices that we had from from Wednesday, big theorem 8 in chapter 1. What's equivalent to being invertible? Giant list of things. Give me some of them. If I do reduced to echelon form, I get the identity. What else? My columns are linearly independent. What else? Lots of other options, right? The one I'm remembering right now is equivalent to both of those is that I have 3 pivots here. So instead of doing reduced row echelon form, let me just do row echelon form. Row echelon form would make this these 3 numbers into zeros. There's a lot of work to do that, right? So there's a lot of algebra. When I do that, which I did in a separate handout on our Canvas page, I get this. Problem is, that bottom expression in the lower right corner here, that actually is disgusting. And all I need to know is if that thing is 0 or not. So really, if that's 0, then I don't have a third pivot. Since this contains that number, that alpha's in both of them, I knew that wasn't 0 to start with. I would have switched rows, right? So it's really just this corner that's the problem. And that's on our reference file section labeled determinant calculation, if you want to see that entire thing. I end up with the following 6 triplet expression. Now, I must tell you, I hate this expression. White hot passion of 1,000 suns. I hate this. But look at this. That one number determines everything I want to know about whether or not this matrix is invertible. This is my expression for the determinant of that 3 by 3 matrix. All right. Since I already told you this is disgusting and I hate it, there's got to be a better way to deal with this. And let me look just at the first two pieces of this. Those have A11 in common, right? If I were to factor that A11 out, I would have this expression, right? Notice what the numbers in the parentheses look like. I've seen an expression that looks like that before. Two numbers multiplied together, subtract two numbers multiplied together. AD minus BC. What if those were AD, BC? A, D, B, C. Huh. Go back to the original matrix. The 3 by 3 at the top of the screen. These four numbers are all arranged up here exactly the way we just set them up, aren't they? I can't have the same number in here twice. The reason I was about to say is look at the bottom two. The last two in this set also have the A13 in common, don't they? If I pull that out, AD, B, C. And what's more, two, 1, 2, 2, 3, 1, 3, 2. These are both submatrices inside the other one. What about this? Minus sign's in the wrong place, isn't it? If I just factor out the 1, 2, then this first term would be negative. Factor out the negative as well. Oh, it helps if I put it in the right order. Let's try that again. minus A12. Then it's A21, A33 minus A23, A31. It helps if I keep the things in the right freaking order, doesn't it? A21, A33, A23, A31, AD minus BC, only instead of having the plus, it has the minus in front. Hey, wait a second. Is this a subset of what's in that first one? Aha! I think I see a pattern here based on this and this, this and this. Let me write down the whole original matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. There. The number outside is A11, right? In this little matrix, circle A11. Then scratch out the rest of the first row and the rest of the first column. There is the little submatrix, isn't it? In this one, the number on the outside is A12. If I circle that and scratch out the rest of that row and the rest of that column, the only four leftover numbers are exactly the four numbers I used here. How about this one with the A13? Does it work the same way? If I circle A13, cross out the rest of the third column and the rest of the first row, the remaining four numbers are exactly the four numbers I used in this determinant. These submatrices are called minors. So it turns out that the way I build this determinant expression is to find across the top row the set of minors and to compute, instead of one bigger determinant, three smaller determinants. And those smaller determinants come from crossing out the row and column from the number that's on the outside. Our textbook calls these Aij with a capital A. So it refers to this as A11, and this is A12, and this is A13. Some textbooks, because these are minors, call these M12, I would say M11, M12, and M13. Either way, the important part here is to remember that we get them by eliminating the row and column from the outside number. Questions? This looks crazy. Let's take the determinants of this matrix. I'm going to use this expansion right here. So, across the top row, I write down the 3, and then I write the sub-minor 3, 2, 5, negative 1. I want that determinant. Move over.
Do we have the brackets?
These are straight lines because that's a determinant still, right? That's the whole point, that we're calculating a number when all is said and done. So this is still a straight line. 0 times. This time it's the cross out the first row and the middle column. So I'm left with 2, 2, 0, negative 1. Plus 4 times 2, 3, 0, 5. And for each of those 2 by 2s, it's AD minus BC. I really don't care what the middle one is because I'm multiplying by 0. But I'm just going to be anal retentive and do them all anyway. 3 times negative 3 minus 10. 0 times negative 2 minus 0. Plus 4 times 10 minus 0. 3 times negative 13 is negative 39, plus 0, plus 4 times 10 is 40. My answer is 1. This matrix is invertible. How would I find the inverse? The formula would only work for 2 by 2s, right? Put the identity on the augmented side, and I do all the row operations I need to, right? But I now know, even before I do that I can actually get an inverse. Questions?
To get the inside the parentheses things, use the ABPC.
Yep. Each and every time, AD minus BC. Then I have a question for all of you. Plus, minus? Why? Who came up with that crazy idea? It turns out that there needs to be a tweak to just doing the cofactors, the minors, and multiplying. You can't just add them all. That minus sign is actually important. But it comes from the sum of those two numbers. So that AIJ number, in this case, negative 13, in this case, negative 2, in this case, 10, those are the numbers we get by doing the little 2 by 2 determinants. whether or not that should be added or subtracted is found by taking a -1 and raising it to the sum of those I and j numbers. If that's even, we're going to get a plus. If that's odd, we're going to get a minus. 1, 1, that's a plus. 1, 2, -1 to the third is a minus. We're going to call this Cij, the cofactor. And all it is a plus or a minus stuck onto the minor. So you'll often hear this expansion called the expansion by cofactors and minors. I must tell you, though, I tend not to remember it this way because the upper left is always 1, 1. That's always a plus. If I move over one column, I've added 1 to the power, haven't I? That's going to switch from a plus to a minus. I move over again. The top row is always plus, minus, plus. Every time I move from this, I change signs. So if I went down, that would be a minus. And then a plus, and then a minus. It looks like a checkerboard. And here's the best part. I went across the top row, right? There's no requirement. I can switch rows, I can switch columns, right? I can go across any row or down any column. As long as I follow the pattern for the pluses and minuses and write down the minors correctly, I will get the same answer. All right, what was our example previously? We had A was 304,232,05, -1. We went across the top row and got 1. You want to do another row or do you want to do a column? Which one? 1, 2, or 3? Column 2. So I'm going to go down column 2. Okay, if that's the case, look at my signs. The first one's a minus. -0 times 2, 2, 0, -1. Plus 3 times 3, 4, 0, -1. Minus 5 times 3, 4, 2, 2. To get each of the minors, I covered up that row and that column. So this is first row, second column. I was left with the outside 4 numbers in the bottom 2 rows. Here I covered up the second row, second column, so I was left with the outside corners. Here, bottom, so I got the upper 2 in the outside 2 columns, 3, 2, and 4, 2. Let's work through the numbers. This is -0 times -2 minus 0, that's 0. 3 times -3 minus 0, minus 5 times 6 minus 8.
Did you want to rearrange rows? Could you put all the zeros at the top and the 8 zeros at the bottom?
I have to rearrange the whole row, right? I can't move individual numbers around. That does change things substantially. But this is 0. 3 times -3 is -9. Minus 5 times -2, that's -9 plus 10, that's 1. There are 4 other ways you could do this. Each and every one of them will give you a 1. The top version of this formula fixes a column J and goes down that column. The bottom version fixes a row I and goes across that row. And because I've written C instead of M, that includes the pluses and the minuses in it. Son of a... Questions? Calculate for me. Give me a determinant. Is this matrix invertible? You can go across any row. You can go down any column. It's completely yours. Oh, which way did you go? Great. 2 times 1, 2, 3 minus 1 minus negative 2 times. That's where the plus minus. Now I'm going to get 3, 2, 1, negative 1 plus 3 times 3, 1, 1, 3. Negative 1 minus 6. Again, plus 2 because the minus subtract cancels. Negative 3 minus 2 plus 3 times 9 minus 1. 2 times minus 7 plus 2 times minus 5 plus 3 times 8. Minus 14 minus 10 plus 24 is 0. This matrix is not invertible. Now, go back to our big giant theorem. These columns are not linearly independent. These do not span the appropriate R3 space. The reduced row echelon form will not be the identity. I'm missing a pivot somewhere. I don't know, but all of those things are now equivalent to one another. There are infinite many solutions or no solutions for any particular vector set this equal to, right? As a transformation, it's not one-to-one, not onto. All of those things now from one calculation. I would point out to you, though, that this process, as described, is recursive. Now, again, the same statement is true. I can go across any row, I can go down any column, I can do this in any bloody order I want. But if I go across the top row, I'm going to get 4 3x3s. If I go down the first column, all 4 of them will have a non-zero number in front of them. If I go across the top row, only 2 of them will have a non-zero number. But if I go across the third row, only 1 of them will. So it is to your advantage, as Ben tried to do earlier, to look for all the places, oh, there are a whole bunch of zeros. Let me expand my cofactors and minors along that row or down that column. So in this case, I would say, let's start with row 3. Gesundheit. And then this determinant. Okay, does it start with a +3 or a -3? Because we count down from here, plus to minus, minus back to plus. Then I get a 3x3. I cross out the first column and the third row, 0, 0, 5, 7, 2, -5, 3, 1, 7. Now, by the way, there should be 3 more 3x3s here, right? But this one will have 0 times whatever. This one will have 0 times whatever, and this one will have 0 times whatever. So who cares? You could put any number you want inside those parentheses. They're not going to affect my determinant at all. So, come on. But now I have a 3x3. What's the best way to expand that? Because I got 2 zeros in the first row. Notice that 3 stays out in front. Plus, minus, plus 5 times 7, 2, 3, 1. Again, there should be 2 more submatrices, 2 more cofactors, but they both have a 0 in front of them. So they're irrelevant at this point. 3 times 5 times 7 minus 6 is 15. This matrix is invertible. Poof. I don't care how big it is. If I make good choices about which way to expand, I can remove a lot of calculation. I think this one is problem 13 in the text. So if this is our matrix A and I want the determinant of this matrix, which way are you going to expand? Or either way, you only have one number that's non-zero, right? So you have options right away. If we do along row 2, then the remaining submatrix so I get plus, minus, plus, minus. Then I get a 4x4. You need to cross out the second row and cross out the third column. Well, now what do you want to do? Right. So whichever one you did first this last time, you do the other one this time. Again, I carry one non-zero number, and we keep going, right? Eventually, by the way, I think the answer to this one is 6. You should finish it out. Make sure I'm not blowing smoke. Questions? Even before I calculate the determinant, this matrix has a wonderful property. What kind of a matrix is this? Reduced. And it has the right number of pivots. It should be invertible. I don't have to do anything else except look at it. But I've actually asked you to calculate the determinant. I know the answer should not be 0. So let me think about the best way to calculate this. What expansion should I do? Row 4? Absolutely. Or column 1, right? One of those two. If I do row 4, plus, minus, 0, plus 0, minus 0, plus 3 times. 3, 5, minus 6, 0, negative 2, 3, 0, 0, 1. Hey, wait a minute. That minor is still in reduced form, isn't it? It's still row echelon. It still has the right number of pivots. Best way to do that one. Let's stay with it. Let's go across the bottom row again. Plus, minus, plus, minus, plus. Now, normally at this point, we'd say it's AD minus BC, right? I'm going to be a pain in the ass. Please notice that that is really an expansion across the bottom or the top row, right? Cross out the row and the column, and you're only left with one number, so it would be 3 times negative 2. Cross out the row and the column, and you're only left with one number, so it would be 5 times 0. AD minus BC is still an expansion by cofactors and minors, but your minor is a single number. Three times minus 2, 0 times 5, right? Wait a minute. This doesn't matter. So this is 3 times 1 times 3 times minus 2. Three, 1, minus 2, 3. Those are the numbers down the diagonal. That is not a coincidence. Every one of our expansions left you zeros in the bottom left, and only the multiplication in the AD direction counted for anything. If the matrix A is a triangular matrix, We described this before. What does it mean to be triangular? You're drawing in the air. Tell me what you're drawing. That's what a shape means to be triangular. What does a matrix mean to be triangular? It means that all the entries either below that main diagonal are 0, or all the entries above in that little triangle above or below are 0. So if A is triangular, whether it's upper triangular like this one is, or all the numbers are under or on the diagonal, then the determinant of A is the product of the entries on the diagonal. Like a capital Greek letter sigma meant add them all up, a capital Greek letter pi means multiply them all up. So that symbol means multiply A-I-I, where I goes from 1 to n. So A11 times A22 times A33, that's exactly what the diagonal entries are.
So if we have a problem, can we find a reduced echelon form and the numbers move across?
But if I do the reduced row echelon form, all of those pivots become?
Not the reduced row echelon form, just row echelon form.
That's a good question. Does doing row operations change my determinant? I don't know the answer to that yet. It would be really nice though, wouldn't it? If I could do the row operations to get rid of a bunch of things and then just multiply. I have to figure out what effect looking at row operations does to determinants. And that's going to come down to looking at elementary matrices. So it's a good thing I already mentioned those, right? Other questions? Promise I will get there. It turns out that I can actually get a little easier. If I have a row of zeros, if I expand along that row, it's all 0, right? If I have a column of zeros, same thing, expand down that column. But I also know that if I have a row of zeros, I'm going to be short a pivot. If I'm short a pivot, I can't possibly be invertible. If I have a column of zeros, then the transpose is missing a pivot. We said in our giant theorem, the last thing we said was if A was invertible, then A transpose was invertible. So all of that can be written in the same format. If A has a row or column of all zeros, then the determinant of A is 0. Each and every time. By the way, for those of you who have taken vectors in physics or in Calc 3, this determinant idea is the same way we did a vector cross product. Torque as a cross product of vectors works exactly as this determinant. But that was 3 by 3. It turns out for 3 by 3, there is actually a shortcut that kind of matches our down and up idea. It's called the rule of Saris. Unfortunately, nothing to do with the candy people. Wrong Saris. This was developed by a Frenchman, Pierre-Frédéric Saris, in about the early 1800s. And he noticed that you could get the same things that we needed to multiply together. Remember the A11, the A22, the A33, those things could be multiplied together if you actually had 5 columns instead of 3. So he said, let's take the first 2 columns and copy them over. Over here. And Sarah said, hey, wait a minute. If I think about going down, like we did with AD, I see here A11, A22, A33 in that line. I see here A21, A32, and A13. And then here, another. Multiply the numbers on each of those lines. So I have 1 times 3 times -2. That's a -6. I have 0 times 2 times 0. That's a 0. I have 4 times 2 times 5. That's a 40. Now let's do the same thing, starting in the bottom left corner and going up, like we did with the BC. So I'm going to take these 3 numbers and multiply them. And these 3 numbers. And these 3 numbers. So I get 3 numbers now at the top here. What are they? AD minus BC. Add the numbers we got going down, subtract the numbers you got going up. -6 plus 0 plus 40 minus 0 minus 10 minus 0. The 3 numbers that went down are all added on. The 3 numbers that went up are all subtracted. -6 plus 40 minus 10 is 24. That's the determinant of our matrix. 3 down, 3 up. When I get to 4 by 4s, it doesn't work anymore. Because a 3 by 3 only had 6 pieces. A 4 by 4 has 24 pieces. I would only get 8 down and 8 up. That wouldn't work. I'd be missing a bunch of pieces. So this is a shortcut, only useful for 3 by 3s. In the last page of this section, there's a way to estimate the size of your determinant based on the largest entries within the matrix. This is particularly useful if you just want to have a range for the numbers. It's on, in my book, it's on page 176, but I just realized that the book numbering is less important to you all. So chapter 3, section 2, right? No, 3.1. 3.1. How big can a determinant be? It's labeled here under reasonable answers. I think you should take a look at that and read that over. I hope you all have a wonderful rest of your day. I will see you on Wednesday.